Hi everyone. This is our look at reaction pathways and catalysts. A reaction pathway has so much in common with a potential energy diagram, just has a little bit of extra information. Just like a potential energy diagram, it has these two horizontal lines. Whether it's endothermic or exothermic, these two horizontal lines, and an up graph is endothermic, a down graph is exothermic, with the distance in between the two horizontal lines, the delta H. These reaction pathways have an extra bit of information in it. You can see there's this extra shape to the graph. This represents what we call the activation energy. It's the minimum amount of energy required to initiate a reaction. To set a reaction off, we have to put a little bit of energy in to activate the reaction. All reactions have this activation energy. Endothermic reactions have it. Exothermic reactions also have an activation energy. All reactions have it. The activation energy, moreover, is always a positive value. It always represents an up movement in the graph. Here we are, we went up for that activation energy. Here, even though in the end, the exothermic graph comes down, there's initial upward movement, the activation energy. The larger the activation energy is, the slower the reaction takes place. And we can read these reaction pathway diagrams from left to right in a forward direction, or we can read them from right to left in a reverse direction. So there's always a forward and a reverse activation energy. Let's think about the endothermic situation first. The graph overall from horizontal line to horizontal line is up. It's endothermic. The distance between those two horizontal lines is the delta H, the enthalpy change, the change in potential energy. But from that first horizontal line, from the reactants up to that first peak, is what we call the forward activation energy. If we're reading the graph in the opposite direction, starting from the products, then we have the reverse activation energy. The idea is, if we have this graph presented to us, we want to be able to pull those three numbers out of the graph. We're just going to read the axis to decide the value. We just have to make sure we're looking at the right part of the graph. In addition, if we have 2 out of those 3 numbers, we need to be able to find the missing number. It's the same idea in an exothermic situation, only the graph overall is going down. From horizontal line to horizontal line, a downward move is exothermic. And just like always, the distance in between the two horizontal lines is the enthalpy change, the delta H. This exothermic graph, it also has a positive forward activation energy and a positive reverse activation energy. An extra point to highlight is that in an endothermic situation, the forward activation energy is always going to be greater than the reverse. Look at how tall that one is. It's actually greater than the delta H, definitely larger than the reverse activation energy. It's the opposite in an exothermic situation. The forward activation energy is small compared to the reverse activation energy. An extra thing that can be added to these reaction pathways is the presence of a catalyst. A catalyst is a chemical added into the reaction vessel, into the container, It's going to speed up the reaction. It's going to reduce the activation energy. We said earlier that the larger the activation energy, the slower. So if we can decrease the activation energy, it will accelerate the reaction. Even though catalysts are going to be present where the reaction is taking place, they're not actually going to take part in the reaction. They are not a reactant themselves. They are not consumed by the reaction. And as a result, they are reusable. An extra important final point to highlight is that catalysts do not affect the overall enthalpy change. They only reduce the activation energy without affecting the delta H. We say that they provide an alternate pathway for the reaction to follow. I like to think of it as a shortcut. Here, my two reaction pathways do not have a catalyst on them right now. Let me add one. We're not going to affect the delta H. We're going to lower the activation energy and provide a shortcut from the reactants to the products, an alternate pathway. It might look like this. I need to color that in. There is still an activation energy. It's hard to notice, but the peak of that one is still higher than my products line. I would not have to write that line in myself. It would be given to me like that, and I would be interpreting what I see. Notice that the delta H was not changed. The distance between the two horizontal lines was not affected by the introduction of a catalyst. What was affected was the activation energy was reduced. The forward and the reverse activation energy were decreased, and that's going to speed up the reaction. We provided an alternate path, a shortcut, to get from the reactants to the products. In an exothermic reaction, it's very similar. There is still an upward movement, a forward activation energy. However, it was reduced. The distance in between the two horizontal lines, the delta H, was not affected. An alternate pathway was created to speed up the reaction. If a reaction does not have a catalyst, we call that uncatalyzed. When there is a catalyst present, we call that catalyzed. So in a situation like this, we might be asked, what is the delta H of the reaction? What was the forward uncatalyzed activation energy? Or what was the forward uncatalyzed activation energy? In a subsequent video, we'll see how we can pull numbers out of these graphs to answer those kinds of questions. But in order to do that, we really need to be clear which area of the graph, which area of the reaction pathway we need to focus on. To wrap up, reaction pathways are just slightly fancier potential energy diagrams. The way that we determine the delta H is the same. The way that we identify endo or exothermic reactions is the same. What is new is this idea of activation energy. All reactions have it. Endothermic and exothermic reactions have it. It's always a positive value. It's always an upward move on the graph. An introduction of a catalyst can slightly complicate our lives a little bit. However, as long as we know which part of the graph is labeled, how each part of the graph is labeled, we'll be able to get the information that we need off of the graph. And I hope that helps.